Welcome to a video on conic sections, namely the parabolas. So a parabola is created from a conic section if you take a two-dimensional surface and cut through the cone's base, but not at 90 degrees like the hyperbola was. So hyperbola was at 90 degrees, so it actually had two parts, above here and below here. With a parabola, because it is going through the base, it's not going to touch the other cone at all. So we get a curvy parabola out of that. So you've studied parabolas in grade 10, but this time we're going to also talk about not just vertically oriented facing up or down, but we're going to also discuss how parabolas can be facing left or right. So briefly, where this is used in real life, a parabola has an amazing property. Any ray parallel to the axis of symmetry, so axis of symmetry goes through the vertex and just goes through like this. And so any ray that's parallel to it, as shown in the picture, is going to get reflected off of the parabolic surface straight towards the focus point. And there's going to be one focus point for parabolas. And that explains why the dot is called the focus, because it is where all the rays get focused. So where is this used? Satellite dishes, radar dishes, concentrating the sun's rays to make a hot spot, the reflector on spotlights and torches, etc. Let's start with some definitions. So vertex and focus point we've seen before. Now we're going to read a little bit about directrix. So all the conic sections do have a directrix, or sometimes several, two of them, but I didn't really need them to develop the equations. But with parabolas, I do need the directrix in order to develop the equation itself. So here's the reason why. Because the parabola is defined as a set of all points whose distance from a fixed point, called the focus, is equal to the distance to a fixed line, called directrix. So let's see how that actually plays out. So if I had a random point A on the parabola, then this distance d1 from the focus to that point, and then at 90 degrees, remember distance usually is the shortest distance, so at 90 degrees over here, down towards this directrix green line, those two red lines are equal in length. But it doesn't have to be this point A. It could be any random point on the parabola. So let's take another one that is oriented horizontally in line with the focus point. So if point B was over here, then this distance d3 and this distance at 90 degrees towards the directrix is d4. These two distances would be equal to each other. And finally, let's put a point right at the vertex itself. So the distance from this point up to the focal point, and from the vertex down to the directrix, d5 and d6 are also equal to each other. Now, what we want to talk about is what is this specific distance in blue that I had is actually equal to. So I said it's equal to P because if the vertex is at the origin, so if this vertex was 0, 0, then the focal point will be defined P distance away from the center. And then because it's equally distanced back and forward, the directrix itself is also P units to the other side. So the blue distances are size P, but I cannot say that the green distances are the same, because that's not what the definition says. It's just the D3 with D4, they could be longer, as obviously you could see it's longer, but they're equal to each other. So let's talk about this specific orientation. We want to know another definition. There is a line that is called latus rectum. So it is a chord of a conic section that passes through a focus and is parallel to the directrix. So let's draw this in. So this is the light blue line over here. So this length right here would be the latus rectum LR. Okay, so it is parallel to the directrix and it goes through the focal point. So the size of this would be 4P. Why would that be 4P? Well, if you look at from the vertex down through the directrix, well, that's size P. And from the vertex to the focal point is also size P. That means this is 2P. And we know D4 is the same size as D3. So from this center of the focal point to point B, that's 2p. And because we're going all the way from this edge all the way here, that would be 4p. So the size of latus rectum will always be 4p. So what we're going to do now is develop the formula. Where does the equation of a parabola come from? Again, what I'm going to do here, you will not be required to do on your own, but just follow it along and see if you can, if you understand the steps. We're going to again do an equation centered at the origin because it's easier, and we'll start with saying that any random point on a parabola, the distances from focal point to that point and from that point down to the directrix at 90 degrees is always going to be equal. So if we're centered the vertex at the origin, and we'll go size p up towards the focus point and call this random point xy, and then this point on the bottom would have to be x horizontally, right? Because it's right underneath point A, but it will be negative p down from the origin. So from the origin down p, so that's why it's negative p here. So now that we have the coordinates in place, we can use the distance formula that we've used before. And notice my notation using vectors. If I said the distance from point A to point F, I could call it a vector or look for its magnitude of the vector itself. Okay, so whichever way, it doesn't really matter. It's just distance formula. So D1 and D2 are going to be these two quantities, and I'm going to use distance formula for both. So let's take a look from A to F. So it's x minus 0 subtracted and squared, plus y minus p. So this is the y over here, this is the p over here, subtracted and squared. Then the distance from A to E. So the point E is over here, so x minus x, so that would disappear. And then y subtract negative p, so that's a double negative there that we will simplify. Again, we want the equation to be as simple as possible so we can square both sides to get rid of the square roots. So this is much easier than the other videos on ellipses and hyperbolas because we only have one term per side and both of them have square roots. So how does this simplify? Well, the square root will disappear from both of them. This term right here is just 0. This y double negative will be y plus, and then x minus 0 is just x squared. Then we will expand each of the binomials with a square. So this would be y times y will be y squared, y times negative p twice because we need to do outside and inside together, so negative 2py, and then negative p times negative p will be p squared. Do the same thing for this binomial with a square. Then you'll notice how both sides have y squared and the p squared. So we can subtract from both sides y squared and p squared. And then we can just put all the terms with y on one side and all the terms on the x on this side. So just moving this term to that term, collecting like terms, we have negative 2py on this side and positive 2py on that side. So in the end, it will be positive 4py. Or if you were to isolate for y, you would have this relationship here with x squared being above 4p. Now, in grade 10, you used to learn parabolas with the equations with a stretch factor that we called a. So this is equivalent. If you do use coefficient a instead, then just know the relationship between a and the p will be 1 over 4p to get the a, or p will be 1 over 4a, whichever one. They're the same equations. Just a quick reminder, remember how we're doing this centered at the origin. So if the parabola was not centered at the origin, you've studied this formula before, that y equals a bracket x minus h all squared plus k. So that's centered at vertex of hk. Please note that this plus k here could also be recorded as y minus k over here. So it kind of resembles what we used to have with circles, ellipses, and hyperbolas. We always had x minus h and y minus k. And then finally, we want to also say that over here we developed that latus rectum length would be always 4 times p, Well, this relationship between the coefficient on x squared and the coefficient that we got with the p here will actually tell us that the length of latus rectum will always be 1 over a with absolute values, because technically this coefficient here could have been negative, but the latus rectum distance is always positive. So these bars over here just say ignore the negative if there is any negative. All right, so what's next? The last thing left is how to draw them. I'm going to do two of them. Notice how one of the equations here has x with a square and y is without a square. And then this second one is the other way around. X is without the square and y is with a square. So I have a summary over here. We can have direction of opening up and down. So this is what you've usually seen for parabolas that are functions. But we can also have parabolas that are going to be oriented horizontally. So they could be facing to the right or to the left. These bars right here, they're supposed to be absolute values. Okay, so here we go. Let's talk about the variations of the equations. So first of all, if you have an equation if it's reorganized in such a way that it looks more similar to this version, and then we can use the p instead of using the a in the equations. And if that's something that you prefer, then here are all the equivalent statements using p instead of a. So latus rectum would be just 4p, absolute value. The directrix equation would be k minus p, because p is equivalent to 1 over 4a, etc. So I'm not going to go over too much of that, because you can just figure it out on your own and use this as reference. Again, I'll repeat, if I asked you to do this on assignment or the test, I will provide you with the formulas. No need to memorize, just know how to use them. All right, so I'm going to talk about this first equation first of all. So it could be given to you in this format, or imagine if you were to move 5 to this side, so add 5, and then multiply both sides by 4. So this equation is equivalent to this version. So if you prefer this top equation, then you're thinking that a is a quarter. And if you have this version, then you're thinking that this 4p over here matches to 4 here. That means that p is actually going to be 1. So here it is, I'm showing you over here. So it's 4 times 1 would be the 4 and p. So p would be 1. Regardless how you're thinking about it, you know that vertex is always hk. So if you're looking at this original equation, you'll say, okay, negative 2 here becomes positive 2, goes to the right. We've learned that before. And negative 5 would be your vertex y position. Or if you're looking at this version, you're thinking it always switches signs. So if here we have x minus 2, that means it's 2 for the x component, or I should be saying coordinate. And then y double negative 5 here to create that plus sign. So the y coordinate of the vertex is negative 5. So then, as I already mentioned, a would be 1/4 if you're looking over here, or p would be equal to a 1, whichever way you prefer. So now we're going to plot it. So here we have the vertex, so v for vertex right there, plotted. You can see it went 2 to the right and 1, 2, 3, 4, 5 down. And then the focal point will be 2 and negative 4. How come? Well, because here x is the one that's squared, then we're following these equations over here. And the focal point would be k plus the p. So whatever p is for us, which is 1 for us, so negative 5 plus 1 would be negative 4. Or you could use alternatively this formula, k plus 1 over 4a, but a is a fraction itself. So using p is actually more convenient, then you'll have less fractions to work with. So once you've plotted the focal point, then you want to use the latus rectum length to figure out 2 other points on the parabola. So why is latus rectum 4? Well, we know that latus rectum length is going to be 4 times p, and if p was negative value, we just put absolute value on it. So we just want to have size 4 altogether. So notice from you're doing this latus rectum through the focal point. So you're going to go 2 units to one side and then 2 units to the other side. So in total, that's 4 units. And that's going to give you 2 more points in the parabola that goes through the vertex, and that finishes off your U shape of a parabola. Now, parabola is different from hyperbola because this parabola will just keep curving out and out and out. It will not ever really look like a straight line, unless, of course, you zoom in on it, and then it kind of looks like a straight line, but it's not technically going to approach a specific asymptote line. And then finally, make sure, because the instructions are to show all the information and sketch, please still show the directrix equation as well as put it on your picture. So the size from the vertex to the focal point was 1 unit. That means you go to the other side 1 unit and draw a directrix line that is parallel to latus rectum. And the equation of a horizontal line will be y equals -6, because this dotted line right here touches at -6 on this. So let's count down 1, 2, 3, 4, 5, 6. Yeah, so -6. So that one's done. Let's do the second one in green. So this particular equation has y being squared. So if it's y being squared, that means it's going to be a parabola that is oriented horizontally, either opening left or to the right. So of course, again, you can change it so that you're not working with the a coefficient, but rather working with p. Then it might be convenient to move the 7 first to the other side, so make it plus, and then multiply both sides by -2. So this is the equivalent version of that equation. Then the vertex is going to be what is subtracted from x here. So there's a double negative there, so it's going to be a -7. So x subtract 7 is equivalent to +7. And then y subtract -4, so that means this would be vertex -4. So you plot that vertex right there. Then you could also consider, because I'm using this other version, because this other version has 4p as a coefficient on a term that's not squared, you're thinking, what is p then? 4 times something has to be -2. Well, that something has to be -1/2. And so you could say that either a is -1/2 or p is -1/2 as well. So in this case, both of them end up being fractions. And there is a negative sign as well. So that negative is going to tell us how to orient that parabola, okay? Next, we want to figure out where the focus point is. So focus point equation up here, h plus p. So h for us is -7 plus -1/2. That would be -7.5. And so you could plot it a little bit to the left of the vertex. The length of latus rectum would be 1 over a, or if you want to think about it as 4 times p, whichever way you think about it, ignore the negative for the distance, is going to be size 2. So from the focal point, go up 1 square and down 1 square for a total distance of 2. Where those two points end, that's where the parabola is going to touch. So that's the 3 points of the parabola, one here, vertex, and then another one at the latus rectum endpoint. And then finally, draw the directrix. Sorry, it's supposed to be completely vertical. It's a little wonky here, but that size here is just half a square over, and the equation of equation of a vertical line is going to be x equals -6.5, because if you were to extend this dotted line over here, that would be exactly where -6.5 is on the x-axis. So this is what you would be required to do to be able to state different things about the parabolas as well as sketch them using this information from conic sections.